Okay, hi everybody. In this module, we're gonna continue and we're gonna look at the pulse transfer function of general open loop configuration, and then we're gonna look at the pulse transfer function of closed loop sample data system, and then we're gonna also look at the state space representation. Now, just to tell you where we are in the course. So far we've been trying to represent different components of the sample data system. In this module, we're gonna finish the representation and getting the transfer function of the sample data system. And then after this module, we're going to be able to get the transfer function of any system, of any configuration, and then we're going to start looking at the response of the system, then we're going to look at the steady state error, the stability, the controller, etc. Okay, so in the previous module, we looked at how to get the transfer function for a system that have a system delay. So we're going to continue today with, we're going to start with the open loop configuration, and then we're going to look at the closed loop configuration. And our objective is to get the transfer function. And we're going to get the transfer function. Since this is a sample data system, we are trying to get the transfer function as a function of z in the z domain. Okay, so this is the configuration that we're familiar with. We have a transfer function, GP of S. This is the plant of our system. And we have an input that is discrete that we are converting using a zero order hold digital to analog converter. We're getting U bar of T. And then the output of the plant, the continuous time, is a continuous time signal that we are taking through an analog digital converter in order to get the samples, y of k or y star of t. And we know if I calculate the transfer function of the zero order hold and GP of S is gonna give me y of z over u of z, and that is gonna equal to 1 minus z to negative 1, the z transform of GP of S over S. This 1 minus z to the negative 1, and this S in the denominator here is coming from the zero order hold. This will give me the transfer function between the output y of z and the input y and the input u of z. The transfer function between the input u and the output y. Now, one thing we're going to do is, just to simplify the notification, we will implicitly incorporate the zero order hold digital to analog converter with each continuous time block diagram driven by a start variable. So anytime we have a transfer function or a block of the plant of any transfer function, and that is driven by a start input, just like we have here, we're going to combine these two blocks together into one block. So instead of this being a zero order hold and GP of S, we're going to combine them together into G of S. So this is what we're going to be doing. And again, this is just to simplify when we plot the system. If I have GP of S, I have a zero order hold and it's driven by a start input, then I'm going to replace this with G of S. And it is understood implicitly that this G of S has a zero order hold inside of it. So therefore G of S is the transfer function of the zero order hold multiplied by GP of S, which is going to be 1 minus e to negative st divided by s multiplied by GP of S. Okay. Okay, so now we're going to look at open loop configurations, and we're going to try to calculate the transfer function of these open loop configuration. And then we're going to use some of the results to look at the closed loop configuration. So let's start with this first example. So I have the signal E of S. I'm sampling the signal. I have G1 of S. I'm taking the output of the plant, I'm sampling it, I'm putting it through another system, G2 of S, and I have the output C of S. And I want to calculate the transfer function between C of Z and the input E of S. So how do we do that? We start at the output. We can write the relationship as it relates the output to the input using this block diagram. If I look here, C of S is equal to G2 of S multiplied by A star of S. So this equation here is coming directly from here. Now also I have A of S here, the output of G1 of S is equal to G1 of S multiplied by E star of S. So these two equations come directly from this block diagram. Now what I'm going to do, I'm going to take the star transformation. So if I do that, I can write this. C of S is going to become C star of S is going to equal to G2 star multiplied by A star. Since this is already starred multiplied by a function, when I take the star transform of C of S is going to equal to G2 star multiplied by A star. Similarly, if I look at the equation on the right, A of S, if I take the star transform, I'm going to get A star equal to G1 star multiplied by E star. And again, this is from the property that we've seen when we introduce the star transform. Okay, so now what we're going to need is we need to eliminate A star of S because I want to the relationship between E and C. So therefore, we can write that C star of S from here is equal to G2 star, and then I can replace A star using this expression here, and that is going to be G1 star multiplied by E star. So I replaced A star with the expression of A star, which is G1 star multiplied by E star. So therefore, C star is going to equal G2 star multiplied by G1 star multiplied by E star. Now we know if I have the star transform, if I replace E to ST with Z, I'm going to get the Z transform. So therefore, that's what I'm going to do. I'm going to take the C star, replace E to ST with Z. I'm going to get C of Z equal to G2 of Z multiplied by G1 of Z multiplied by E of Z. And therefore, I can get the pulse transfer function C of Z over E of Z, and that is going to equal to G1 multiplied by G2. Okay, let's look at another example. So here, unlike the previous example where we had the output of G1 of S going through a sampler and therefore getting a discrete signal here, in this system we remove that sampler. So we have the signal E of S going through a sampler, then G1 of S, then the output of G1 is going directly through G2 of S, and then I have C of S. Now here, G2 of S does not include the zero order hold digital to analog converter. Why? Because it's not driven by a star input. It's driven by M of S. It's not driven by M star of S. Remember, in the first slide here, we said if I have a transfer function that is driven by a star input, I'm going to replace it, take the zero order hold, and implicitly include it in the transfer function. We've done this here because this is a star. We have a star here. However, here, if I look at G2 of S, it's driven by M of S. It's not driven by M star of S. And therefore, G2 of S does not include a zero order hold. Okay. So therefore, we're going to write the relationship C of S is equal to G1 of S multiplied by G2 of S multiplied by E star. And therefore, if I take the star transform, I'm going to get C star. Now these together are multiplied by E star. So when I take the star transform, I have to multiply them with each other and then take the star transform. And therefore, that's going to give me G1 multiplied by G2 star multiplied by E star. And therefore, I can write C star over E star and then replace E to ST with Z to get C of Z over E of Z. And that is going to equal to G1 multiplied by G2. And after the multiplication, we're taking the Z transform. So therefore, this symbol here, the bar above G1 and G2, means the Z transform of G1 multiplied by G2. After we multiply them, we take the Z transform. And therefore, this transform, G1 multiplied by G2, and the bar above it, is equal to the Z transform of G1 multiplied by G2, and this is not equal to G1 of Z multiplied by G2 of Z. Okay. Let's look at another example. So in this system, we have the input E of S going through G1 of S, the output A of S is sampled to go through G2 of S, and I have C of S. I want to see if I can get the transfer function between C of S and E of S. So let's write the equation for the output. The output C of S is equal to G2 multiplied by A star. A of S from here is equal to G1 of S multiplied by E of S. And coming back here, substituting for A star. So I'm going to take this, take the star for it. If I take the star for it, this is going to give me A star of S is equal to G1 of S multiplied by E of S. And after I multiply them, I'm going to take the star transform. Why? Because none of these, neither G1 of S nor E of S is starred. And therefore, when I take the star transform, I have to multiply them and then take the star transform of them. I hope this is clear. If I had A equal to G1 multiplied by E star, then when I take the star transform, I'm going to get A star equal to G1 star multiplied by E star. So this is one case. Now, if I have A just equal to G1 multiplied by E, when I take A star, is going to equal to G1 multiplied by E, and after I multiply them, I take the star. I cannot separate the G1 and E. I can only separate them, like I did here, if one of them has a star on it. Okay, so coming back here, I have G2 multiplied by A star. A star is equal to G1 multiplied by E, and then after the multiplication, we take the star. I'm going to take the star of both sides. I'm going to get C star equal to G2 star, and then multiplied by G1 multiplied by E. After the multiplication, we're taking the star transform. Now, if I look here, I'm stuck. I cannot separate E outside of this formula, of this expression. And therefore, in this case, I'm not going to be able to write C of Z divided by E of Z. I cannot write C of Z divided by E of Z. Since we cannot factor this E outside before it's multiplied by G1 of S. And therefore, I cannot get a transfer function between C and E alone. I cannot separate the E on the right side because I have to multiply it and then take the star transform. Okay. Now, why is this the case? I mean, just to give you more understanding of why this happens. Why is it I'm not able to write the expression or the transfer function between between C and E of S. The reason is the following. If I take the Z transform of E, E of Z is equal to Z transform of E of T at sampling time. So if I take the signal E of T, take the samples, I can calculate the Z transform from these samples. Now what happens here? I have E of S going through G1 of S to give me A of S. Now when I, at the right side, at G2, I have the samples of A of S that is going through G2 of S. However, the input signal A of T, this signal A of T, is a result of the output of G1 of S when I applied E of S to it. Now, if I have a continuous time system and I have E of S applied to G1 of S, how do I get the output? In the frequency domain, I multiply G1 of S multiplied by E of S. In the time domain, that's a convolution. What is the convolution? So if I look at A of S, this signal here at the output of the first block, A of S is equal to G1 of S multiplied by E of S. What is this in the time domain? A of T is going to equal the integration from 0 to T, G1 of T minus tau multiplied by E of tau d tau. What does that mean? That means every time I'm taking a sample of the signal A, every time I take a sample here, this sample comes not only from E at that time, it comes from E at that time and all the other previous times. Why? Because I have this integration here. I have to integrate from 0 to T E of tau d tau. Does that make sense? Okay, so let me repeat it again. So in this case, where the signal is going directly to the system, to G1 of S, before it is sampled. E of S is a continuous time signal, G1 of S is a system. I'm inputting this signal to this system, I'm going to get an output. The output at any time is a function not only of the input at that time, but it's also a function of the input at previous times. Now when I take the samples here, when I sample at the output, each one of these samples will have a sample of A of T. That sample of A of T comes not only from E of T at that time, but it also comes from E of T at previous times. And that can be seen from this formula for the convolution. The output at any time, if I calculate A of T at any time, at T1, this is going to equal the integration from 0 to T1, G1 of T minus tau, E of tau d tau. Which means not only the signal E at T1 is going to make this output, but also all the values of the signal E at previous times is going to contribute to the output A at T1. And therefore, I cannot get a relationship between E directly and the output C of T or C of S. Okay. So therefore, in the situations where the signal E of S is filtered before sampling, it is not possible to obtain a transfer function of the form C of Z over E of Z. Okay. So now that we looked at some examples of the open loop system, we're going to look at other examples, but now we're going to consider the closed loop sample data system. Now also I realize probably some of these configurations that we might have, you know, a practical applications, and we'll highlight that. Some of them are hypothetical, just to illustrate the calculation that we do to get the transfer function. So keep that in mind. So somebody might be looking at one configuration and say, oh, why will you want to input this signal, sample this signal, and then convert it back to continuous time signal and then put it through the system? Why would you have done that? Again, we've done it here up to this point just to illustrate the calculation, but later on we're going to be adding a filter in between that will alter that signal before it is converted back to an analog signal. Okay, so let's look at this configuration. We have a closed loop system here. I have a set input. I mean, you probably this feedback loop is familiar to you. We have a set input R of S. I have the output. I'm feeding it back, multiplying it through a transfer function H of S. I'm taking the difference, subtracting R minus this signal that I fed back to get the error signal E of S. I'm going to sample this signal E of S. I'm going to get, this is sampled every t seconds. At the output of the sampler, I have E star, and then I'm going to apply this to my plant. Now again, because the input here is starred, I'm going to assume, or I'm going to implicitly assume that this G of S contains the zero older hold. So this G of S is made of two blocks, one of them zero older hold and GP of S. Together they are G of S. And this is my output, C of S, and I'm going to calculate the closed loop transfer function. Again, you can look at this configuration. I'm taking a continuous time signal, I'm converting it to a discrete, then I'm converting it to a continuous signal, and I'm applying it to the plant. What's missing here is a filter that I can apply to the discrete time signal that I've sampled. But for the time being, for the sake of doing the calculation, we're going to just look at this configuration here. Okay, so how do we get the transfer function? C of Z over R of Z. C of S is equal to G of S multiplied by E star. This is here. Directly, C of S is E star multiplied by G of S is going to give me C of S. And also, we know that E of S is equal to R minus H of S multiplied by C of S. So this is the second equation. The error signal is equal to R minus H multiplied by C. Okay, so from these two equations, I can come to this equation here. E of S is equal to R of S minus H multiplied by C of S. But C of S, using equation 1, I can write it as G of S multiplied by E star. Again, this is from the first equation. So now I have this equation. I can take the star transform of both sides. I'm going to get E star equal to R star minus, if I star this term here, this has a star in it, so I can separate it from the other terms, but these two terms have to be multiplied together and then have to be starred. So I'm going to have H of S multiplied by G of S starred multiplied by E star. And therefore, I can write E star is equal to R star, move this term to the other side, take E star as a common factor, and then divide by that common factor that we've taken. We're going to get E star equal to R star divided by 1 plus HG star. Of course, the star here after we multiply them. Now, if I take the star transform of 1 and substitute for E star, so I'm going to go back to equation 1. C of S equal G of S E star. If I take the star transform, C star is equal to G star multiplied by E star. But E star, we calculated it, and it is equal to R star divided by 1 plus HG star. And therefore, I can write C of S divided, C star of S divided by R star of S is going to equal to G star divided by 1 plus H multiplied by G over all star. If I replace E to ST with Z, I'm going to get G of Z over 1 plus HG of Z. And therefore, this is the transfer function between C of Z and R of Z. And notice here, this transfer function, we're going to be able to obtain it after we multiply H multiplied by G and take the Z transform of that. Okay. Let's look at another example. So in this example, we have a continuous input. We have error signal continuous. We're applying it to the system G of S. And then I have the output. I'm taking the output. I'm sampling it to get C star. I'm applying it to H of S. And then I'm subtracting that from the input signal R of S. So let's try to calculate the transfer function, starting with the output. C of S is equal to G multiplied by the error signal. This is equation 1. The error signal E of S is equal to R of S minus H multiplied by C star of S. This is the second equation. Now I'm going to take the star transform of equation 1. I'm going to get C star equal to, now if I look at this equation 1, none of these are starred. So therefore, when I take the star transform, I'm going to have to multiply them and then take the star transform. So it's going to be G multiplied by E. After we multiply them, we're taking the star transform. Now I'm going to take the star transform of equation 2. It's going to be E star equal to R star minus H star multiplied by C star. Now if you look here, we cannot eliminate E star from 4 using equation 3. I cannot substitute for E star in this equation because here I cannot separate from 3. I cannot take E star as a factor out. Okay, so what we can do, let's try to eliminate E of S from 2 using 1. So what we're going to do is that we're going to eliminate E of S from 2 using equation 1. So if I look at equation 1, C of S over G of S is going to equal to E of S. From equation 1, E of S is equal to C of S divided by G of S. Now this is equal to R of S minus H of S multiplied by C star of S. This is equation 2. So what we've done is we just expressed E of S in terms of C over G and substituted for E of S in the second equation here. So therefore, I'm going to have C over G equal to R minus H multiplied by C star. I can multiply it by G, both sides. I'm going to get C of S equal to R multiplied by G minus H multiplied by G multiplied by C star. Now I'm going to take C star, or take the star transform of both sides. I'm going to get C star equal to R multiplied by G. These multiply together. I'm going to take the star transform minus H multiplied by G over all star multiplied by C star. But I'm still not able to factor R from this equation. So if you look here, this is multiplied, and then I'm taking this the star transform. So therefore, we conclude we cannot factor R star from R multiplied by G over all star, and the conclusion is that we cannot find a transfer function C of Z over R of Z for this configuration. So C of Z over R of Z cannot be found. Okay. Okay. Let's look at another example, and before we look at the other example, let's look at the general method for deriving the closed loop sample data system. We're going to draw a block diagram of the closed loop system. We're going to assign variables to each sampler input and output, and we're going to star at the output of the sampler. We're going to have that output starred. Along with the system input, we're going to consider each sampler output to be a source, and therefore we're going to express each sampler input and each system output in terms of that sampler's output and system input. And then we're going to compute the star transform of each equation, octet in 2, and solve for the star transform output in terms of the star transform inputs to that closed loop sample data system, which is the steps that we've been doing. So let's look at this example. So in this example, we have the input R of S, we have E of S, we're sampling E of S to get E star, we have G of S, the output is sampled to get Y star, and we're inputting that through H of S, and we're feeding it back. So applying the steps that we just mentioned, the sampler's inputs are the signal E here and the signal Y of S. The system output is Y of S here, and therefore we can write E of S is equal to R minus H multiplied by Y star. The system output Y of S is equal to G multiplied by E star. Now we're going to compute the star transform of 1 and 2. E star of S is going to equal to R star minus H star multiplied by Y star. Y star from the second equation is going to equal to G star multiplied by E star. Now we can solve for Y star and express it in terms of R star. So Y star is going to equal to G star. I'm going to substitute for E star with the expression that I have in this equation here. So I'm going to get G star multiplied by R star minus G star multiplied by H star multiplied by Y star. So then I'm going to move all the terms that have Y star to the left side. I'm going to have Y star multiplied by 1 plus G star multiplied by H star equal to G star multiplied by R star, and therefore Y star over R star is going to equal to G star over 1 plus G star multiplied by H star. Now we can substitute for E to ST with Z. We're going to get Y of Z over R of Z is equal to 1 over 1 plus G of Z multiplied by H of Z. Okay, now hopefully this reminds you of the continuous time systems. When we used to calculate a continuous time system that has a G and has an H, the transfer function between the output Y over R used to be G over 1 plus G multiplied by H. And here we're getting something, expression that looks similar, but of course it is in terms of Z. unlike the continuous time, this used to be in terms of s, here it is in terms of z. Okay. So again, for this system, we're sampling the error signal, we're sampling the output, we're able to write the transfer function between the output to the input as g of z over 1 plus g multiplied by h of z. Okay, let's look at another example. Now this is a practical example. So let's say we have a computer that we're going to use to control some physical variables. So this could be the plant, could be the temperature in a chamber, the temperature in a room. This could be the position of a motor. This could be the fluid level in a tank. And what we're going to be doing to control it is a computer. And the way we're going to do it is the computer has the set value programmed into what level is going to be used as R as the input, R. And the computer is going to generate a digital signal that is going to be converted to an analog signal outside and applied to that plant. Now the output of that plant that we're trying to control, I'm going to read it to the computer. So I'm going to use an analog to digital converter in order to get the digital signal from that output. So again, everything in the box here represents the computer. So this is the computer that is used to control that plant. I have an analog to digital converter interface here that's going to be reading the current, gonna be reading the output, and I have a digital to analog interface here that's going to be the signal that is applied to the plant. Okay. So if I plot the equivalent block diagram of this system, I'm going to remove the zero order hold and include it into G of S. I have U star, I have C of Z, I have the error signal R, I have the output signal that is sampled to give me Y star, and this is fed back and subtracted from the input R. Now one thing that we see here is I added this C of Z. What is the C of Z? This is my controller. So this error signal that I'm going to be calculating, if I am, for instance, calculating what I'm trying to do, I'm trying to control the fluid level in a tank. This Y is going to give me the current level. And if I have a motor here that is responsible for adding the water, I have the signal that is applied to that motor is going to be coming from the system here, from the computer here, U bar of T. So U star of T is going to be applied to this motor, and the error between where I want this level to be and what the current level is, this is my error signal. So this is my signal that I have the error signal here, E of K. Now, if I know the error signal, I can just apply it directly to the system, to the motor that is going to be adding more fluid, or I can manipulate it and have it changed according to the filter that I'm adding here. And that is why I'm adding this filter. So I'm going to take this error signal, I'm going to apply a filter that's going to take E, the signal, the error signal, and generate U, the signal U at the output, and that signal is going to be applied to the plant instead of applying the error signal. And again, I'm going to use that if I have a certain performance characteristic that I'm trying to meet. If I want a steady state error to be 0, if I want the response to be overshoot, undershoot, etc., I'm going to choose this C of Z in order to meet that performance criteria. Okay, so let's go back and look at the transfer function. G of S, as we said, because it's driven by a start input, is going to equal to the zero order hold and the plant. R of Z, since this is given in terms of Z, R of Z, I can get R star of S by just replacing E to ST with Z. The error signal E of Z is going to equal to E star, again replacing E to ST with Z. C of Z is going to equal to, there is no C of Z. Okay, let me take this off. Okay. What we want to calculate is the Y of Z divided by R of Z. So we're going to express the sampler input Y of S, this sampler, in terms of R star and Y star. So if I come here, Y of S is equal to G here. Y of S is equal to G multiplied by U star of S. So therefore, G multiplied by U star of S, but U star of S is equal, oh sorry, C of Z that I took it out is the filter. C of Z is equal to C star of S E to ST equal to Z, the filter. We're running out of letters. We use C for the output, but here we're using it for the filter. Okay, so here U star is equal to C star, sorry, U star is equal to C star multiplied by E star. U star is equal to C star multiplied by E star. So therefore, this is substituting for U star. We're going to have G of S multiplied by C star, but E star is equal to R star minus Y star. So therefore, R star minus Y star. Therefore, Y of S is going to equal to G multiplied by C star multiplied by R star minus G multiplied by C star multiplied by Y star. If I take the star transform, Y star is going to equal to G star multiplied by C star multiplied by R star minus G star multiplied by C star multiplied by Y star. Okay, so as a result of this, taking the star, G now is start and G here is star. Since the other terms multiplying it are already start, I can separate them. I don't have to combine any together. Then we're going to write V star. If I move this term here to the other side, I'm going to have Y star multiplied by 1 plus G star multiplied by C star equal to G star multiplied by C star multiplied by R of S, and therefore Y star over R star is going to equal to G star multiplied by C star divided by 1 plus G star multiplied by C star. If we substitute for E to ST, we're going to get Y of Z over R of Z equal to G of Z multiplied by C of Z over 1 plus G of Z multiplied by C of Z. So therefore, this is the closed loop expression for this system here between the output Y and the input R. y over r is g multiplied by c over 1 plus g multiplied by c. Okay. Let's look at another example. And in this example, we're going to consider what happens if we have computational delays. So therefore, what happens if, when I'm calculating, for instance, the filter, if the computer is doing the calculation for the signal that's going to be applied to the plant, and the calculation takes a time that is comparable with the sampling time. If that calculation is much smaller than the sampling time, we can ignore it. However, if the calculation is going to result in a computational delay, TC, that is comparable to the sampling time, then we need to account for that delay. So let's look at this example here. We are given that we have a calculation delay that is equal to delta t, where delta between 0 and 1. And we have our system, R of z, E of z, we have the controller C of z, and we have our system here, G of s. And now what we're adding to this is this term here, e to negative delta multiplied by ts. And this is to account for the delay. Okay, so therefore, if I look at y of s is going to equal to g of s multiplied by e to negative delta ts multiplied by u star, and this is going to equal to g of s e to negative delta ts, and u star is equal to c star multiplied by e star. And therefore, this is going to equal to g of s e to negative delta t multiplied by s c star, and the error signal e star of s, e is going to equal to r minus y star. This is y here, this is y, here it is y star. Okay, so therefore c star multiplied by r star minus y star, I'm going to multiply these terms, g of s, e the exponential, c star, r of s, minus g of s, e to the delta, cs, c star, multiplied by y star. And therefore, if I put the terms, put the g of s with the exponential, y star is going to equal g of s, e to negative delta ts star. If I take the star transform of this equation, y star is going to equal to g of s, e to negative delta ts multiplied by c star multiplied by r star minus, again, g of s multiplied by the exponential star multiplied by c star multiplied by y star. Okay, so we can move this term, the one on the right, to the other side. We're going to have y star multiplied by 1 plus this term equal to g star, g of s multiplied by e to negative delta ts star multiplied by c star r star. If we divide by r star, we're going to get y star over r star. And now we have this term here divided by 1 plus that term multiplied by c star. Finally, if we substitute for e to st with z, we're going to get y of z over r of z. And what is the z transform of the g of s e to negative delta ts? We can get that from the modified z transform. This is equal to g of z comma m multiplied by c of z over 1 plus g of z comma m multiplied by c of z, where g of z comma m is the modified z transform, where e to st is equal to z and m is equal to 1 minus delta. Okay, so again, this is the transfer function for a system that has computational delay. Let's look at another example, and this is probably the most generic, or one of the generic configuration that we can have, and this configuration has 2 degrees of freedom. We have HF of Z and HFB of Z, feed forward and feed backwards. Now in this configuration we can select the poles and zeros of the transfer function through the selection of HFF and HFB. We'll see that when we look at the transfer function at the end. Okay. So let's start. Y is equal to G multiplied by U star. U star is equal to H feed forward star multiplied by E star, which is equal to G of S H F F star. E star is equal to R star minus H F P star multiplied by Y star. And if we compute the star transform, we're going to get Y star equal to G star multiplied by HFF star R star minus HFB star multiplied by Y star. And therefore, if I take the ratio Y, of course, if I take this term and move it to this term and move it to the other side, Y star multiplied by 1 plus G FF HFB equal to G multiplied by FF multiplied by R. If I calculate Y star over R star is going to equal to G star H feed forward star over 1 plus G star H feed forward multiplied by H feed backwards star. And if I replace the star transform with the Z transform, I'm going to get Y of Z over R of Z equal to G of Z multiplied by HFF over 1 plus G of Z multiplied by HFF multiplied by HFB. Now if you look at this transfer function, you can understand why we said we have 2 degrees of freedom. I can choose the zeros of this transfer function using FFF, and I can choose the poles of this system using HFB. So using HFF and HFB, I can choose where I want my poles and zeros to be. Now what we're going to be looking at next is we're going to be looking in the next week module, we're going to be looking at the response in the time domain and see how it relates to where these poles are located. Okay. The last thing we're going to look at is how do we get the state space representation of a closed loop sample data system. So let's say that we have a closed loop data system. I have the input is discrete, so I have E of k, we have Y of k, the output is continuous. I converted it using analog to digital converter, and therefore I have the relationship between U of k and E of k is given by the state space representation of the discrete system. This is the controller. So this could represent my controller, and I represented the controller using state space representation, and I'm going to call these delta, the A, B, C, or A tilde, B tilde, C tilde. So we have some states that are coming from the controller. I'm going to take the output, and the output is going to be called U, you're going to be called U of k. And U of k is gonna be applied to the plant. The plant is continuous, so I have AC, BC, and CC. The input to this controller is the error signal E, so that's why this is E here. And I'm assuming there's no feed forward, so I'm assuming the D matrix both here and here is 0. So the output only depends on the states. It does not depend directly on the input. That's why the D matrix in both of these, the plant and the controller, is equal to 0. Okay. So what we can do is we can replace the 0 Alder-Holt digital to analog converter and the continuous plant with the 0 Alder-Holt discrete time equivalent model. So what we're going to do is we're going to take this continuous time and 0 Alder-Holt and replace it with the discrete time equivalent model. And therefore what I'm going to have here is that I'm going to have the states that are coming from the controller, the states that are coming from the plant. These states I'm going to call it tilde, these states I'm going to call it x, and therefore I'm going to have these two state space representation, one for the controller and one for the plant. Now what I'm going to do, of course, I mean, as we know, to calculate these matrices, the A, B, and C matrices, as we've seen in the previous lecture, A is equal E to A, the continuous multiplied by T, which is equal to Laplace inverse of S multiplied by I minus A inverse, and the B is equal to integration from 0 to T, E to AC multiplied by sigma D sigma multiplied by BC, and the C for the discrete is just going to equal to the C matrix for the continuous system. So these are the state space representation ABC for the discrete time equivalent. Now what we're going to do is we're going to derive the model for the sample data system above. What we're going to do is we're going to consider our input. As we see here, the input is R of k. So even though this system has an input E of k, this system or this subsystem has an input that is U of k. For the overall system, the input is R of k. So we have the input R of k and the output of the overall system is Y of k. Now what we're going to do, since we have states that are coming from the controller and we have states that are coming from the system, we're going to combine them all together. The state vector we will denote by P of k will contain the states of both the controller and the plant. So P of k is going to equal to the states that are coming from the controller and the states that are coming from the plant, X of k and X tilde of k. Okay, so if I look here, I can write X tilde of k as equal to A tilde X tilde of k plus P tilde E of k, but E of k is equal to R of k minus C multiplied by X of k. So looking here, E of k is equal to R of k minus the output Y of k, but the output Y of k is C multiplied by X of k. So therefore X tilde of k plus 1 is equal to A tilde X tilde minus this is coming from here, B tilde multiplied by C multiplied by X of k plus B tilde multiplied by R of k. So therefore the state, using the results, the last two results, the state space model for the closed loop sample data system can be written as X of k plus 1 is going to equal to A xk plus B multiplied by U of k. So from here, xk plus 1 is equal to A xk plus B multiplied by U of k. But U of k is the output of this controller. It's equal to C tilde multiplied by X tilde. Together? So this is coming from here, this is coming from here. So therefore I can substitute for u of k with c tilde x tilde. So I'm going to get x of k plus 1, and then x tilde of k plus 1 is equal to negative this equation here, negative b tilde c multiplied by x plus a tilde multiplied by x tilde plus b tilde multiplied by r of k. And the overall output of the system is y of k equal to c multiplied by x of k, this equation here. So therefore I can put all this in a matrix format. I'm going to take x of k and x tilde together, x of k, x tilde. X of k is equal to a multiplied by x plus b multiplied by c delta multiplied by x tilde plus 0 multiplied by r of k. X tilde of k plus 1 is equal to negative b c multiplied by maybe this is easier if I keep this. It's easier to see this if I keep this x of k, and this is x tilde of k. X tilde of k plus 1 is equal negative bc multiplied by x of k plus a tilde multiplied by x tilde plus b multiplied by r of k. Now these together, I call them, combine them together. This is p of k plus 1, and this is p of k. Now the output y of k does only depend on x of k, so therefore y of k is going to equal to c multiplied by p of k, which is, again, we can keep it as p of k, or we can just have it as x of k, x tilde of k, and we're just going to say this is p of k. Y of k is equal to c multiplied by x of k, and 0 multiplied by x tilde of k. Okay, so this is the state space representation of the closed loop system that we have here, where we have a controller and we have a plant, and each one has its own state space representation, and this is the expression for the state space representation for both of them combined. Sounds good? We'll stop here. Thank you, everybody.